Okay, next what we are going to do is to look at some of the learning algorithms and go over them briefly. Remember, the aim here is not to let you master all the details of that, but to let you know what are the key aspects out there. So when you are using a library, you are aware that what are the key information that we are looking at. Remember, each algorithm will have some assumptions. These assumptions are, for example, the data are normally distributed, or the independent variables and dependent variables are linearly correlated, things like that. So remember, all assumptions, like in your data, it might not fully meet those assumptions, but it doesn't mean it can't be used if like a small violation of the assumptions is there. It's your ability or responsibility to make sure to which degree we can use something and not use something, because at the end it's the performance that really matters. Okay, let's look at linear regression, which is quite a good example to get into the details of machine learning. And yes, linear regression is also considered as machine learning or AI, as a simple form. And as you can see, a lot of the statistical methods can be considered as AI in general. Okay, so the assumption here is that the output y is a linear combination of the input x plus some of the error or noise there. So if we get the write it as the y hat, which is the predicted value, the predicted value y hat will be a value which is the intercept here, plus another value which is the slope times the input. So this is the intercept, this is the slope. Now what we can do here is to convert this into an optimization problem. Now one thing you need to realize is that all model chainings are optimizations. All model chainings are optimizations. And the way we convert this into optimization problem is to define a loss. Now the loss is just a distance between the prediction and the ground truth value. Sorry, got a phone call, just muted. So the loss is just a distance to measure the distance of the prediction and the ground truth. So here what we can do is we can let the ground truth minus the prediction square them. The reason we square them is because we don't want the positive and negative errors to cancel out, so if we square them, it will persist there. And then sum it over all the samples. So what it does is basically to get all these distances and then square these distances and then sum them. And at the end, if we substitute this equation into here, so we get this one minus the prediction, the ground truth minus the prediction. And yi and xi are just the ith value of x and y. Remember, in supervised learning, we have the ground truth and the labels. And regression is under supervised learning, so we need to have the y values there in order to train the model. And this becomes like a function of loss expressed as W0 and W1. So what we're trying to optimize is to try to optimize W0 and W1 such that the loss is minimized. To put it another way, what we are trying to do is to find the intercept and slope so that it fits with this general pattern to the largest extent. Okay, that makes sense, right? And how can we find this W0 and W1? Well, there are two ways to do it. One way is to use analytical solution. We can get the partial derivatives for each of these parameters, set it to 0, and then solve it. This works for simple scenarios. Now in linear regression this can be done. However, this cannot be generalized to more complicated algorithms. And for those we need what's called a numerical optimization approach, and this is what I mean by basically all AI models are optimization problems. So we are using numerical optimization approaches to find the optimal W0 and W1. In a deep learning model, this can be millions of parameters, so we are really looking for a combination of millions of parameters such that when we use that set of parameters, the prediction and the ground truth is very close. There are many ways, by the way, in the numerical optimization, and one of the most widely used is gradient descent, which is a very powerful way of thinking the optimization. And this is something we're going to look at next.